Hello students, in the last class we have discussed about the how to calculate the magnetic field in the toroid by using the ampere circuit law. Now next we see one of the example, that is ampere's law as applied to the small closed loop. Okay, so for this you have to consider a Cartesian coordinate system, x, y, z axis. Consider a magnetic field H evaluated at the point shown in the figure. So we can approximate the field over a closed path 1, 2, 3, 4 by making appropriate adjustment in the value of H along the each segment. Okay, so you can see in the figure, so 1, 2, 3, 4 is a closed path, so where we need to find out magnetic field H at a point inside this path. Okay, where H is equal to H naught at that point is given by H x naught Ax plus H y naught Ay plus H z naught Az, and along the path 1 2 delta y, along the path 1 4 it is delta x, that is a differential length. Now the objective is to take the closed path integral and ultimately obtain the point form of Ampere's law. Okay, so this is our objective. So why we are going to consider this small closed loop? Because we need to obtain the point form of Ampere's law. Okay, how this can be done is by taking a closed path integral we can achieve that, right? Next, approximation of H along the one segment. So if you want to calculate approximation of H along the one segment, so along path 1 2 we may write H dot delta L, that is along the path 1 2 is equal to Hy of 1 2 delta y, right? Where Hy of 1 2 is equal to Hy naught plus dou of Hy divided by dou x into bracket half of delta x. So this is a formula already we have studied in the first module of differential volume element during defining the divergence. Okay, so along this path you can get Hy naught component and the differentiation of y component, partial differentiation of y component along with x, and half of delta x, right? And therefore H dot del L is along the path 1 2 is equal to Hy naught plus half of dou Hy divided by dou x into delta x into delta y, right? So it is a total what H along the one segment, that is one path, that is 1 2, right? So this is the equation. Fine. So similarly now contribution of y directed path segments, right? So you can consider the same figure. Now the contribution from front and back sides will be, so here it is the contribution from front side is the same equation which you have seen previously, and the contribution from the opposite side, that is H of 3 4. So H of delta L, that is along the path 3 to 4, this is into bracket H of y naught minus half of dou Hy by dou x into delta x, bracket complete, into bracket minus delta x, right? So into bracket delta y, sorry. So now note that the path direction is specified in the figure and how this determines the signs used. So you can observe the path directions. So in 1 2 it is having in one direction, and 3 4 it is in the opposite direction. So therefore we get a negative value, right? So this leaves the left and right sides, right? Now only thing is we have calculated the H along the path 1 2 and 3 4. Now next we need to calculate the path along 2 3 and 1 4, right? Now contribution of x directed path segments. So previously the contribution was along the y directed path segments. Now it is the contribution of x directed path segments, right? So along the path 2 3, so you can have the h dot delta L along the path 2 to 3, h of x naught plus half of delta hx divided by, sorry, half of dou hx by dou y delta y bracket complete into minus del x. So same thing, whatever your previously equation, your written equation for 1 2 and 3 4, those are along y directed, this is along now x directed. So you'll get minus delta x for path 2 3 and plus delta x for path 3 4, and the contribution from left side, that is path 4 to 1, it is h dot del L, that is 4, path 4 to 1 is nothing but h of x naught minus half of dou hx by dou y delta y to delta x. Okay, what is the next step is to add the contribution of all the four sides to find the closed path integral, right? Now net closed path integral, so the total integral will now be the sum of integration over closed path h dot dl, so is equal to the h dot delta L along all the paths. So there is along the path 1 2 plus along the path h dot delta L along the path 2 3 plus along 3 4 and plus along 4 to 1. And using our previous results, if we combine all these, the equation becomes integration over closed path h dot dl is equal to dou of hy divided by dou of x minus dou of hx divided by dou y into bracket delta x minus delta y, right? So this will get a total integration over the one complete closed path, right? So along the delta x and delta y, right? So if you want to find out the magnetic field along the small closed loop, so you can use this equation. Thank you.